Hey everyone, welcome back to Chem Story. In today's lesson, we're picking up right where we left off, continuing our look at the factors that affect SN2 reactions. In the last lesson, we talked about nucleophilicity and how it affects SN2 reactions. Today, we're diving into three more key factors: the structure of the substrate, the leaving group, and the solvent. Each of these plays a big role in how smoothly an SN2 reaction goes. So let's break them down, one at a time. First up, the structure of the substrate. For an SN2 reaction to work, the carbon that holds the leaving group must be sp3 hybridized. That allows the nucleophile to attack from the backside, which causes inversion of configuration. If the carbon is sp2 or sp hybridized, the reaction either slows down a lot or just doesn't happen. Now let's talk steric hindrance. The more crowded the carbon is, the harder it is for the nucleophile to get in. That's why different types of alkyl halides react at different speeds in SN2 reactions. Tertiary alkyl halides, they hardly react at all. There's just too much bulk in the way. Neopentyl halides are similar. Even though the carbon with the leaving group is primary, bulky groups nearby make it really slow. Secondary alkyl halides react moderately. Primary ones, much faster, because there's less steric interference. Even better, allyl and benzyl halides. They're more reactive than regular primary halides. And at the top of the list, methyl halides. With zero steric hindrance, the nucleophile has a clear shot, and the reaction flies. Now let's take a look at how different alkyl halides compare using actual reaction data. This chart shows the SN2 reaction rates of various alkyl bromides reacting with chloride ions. And the trend? It's super clear. Tertiary alkyl bromides barely react at all. Neopentyl bromides, same story, way too slow. But as we move to secondary, then primary, and finally methyl bromides, the reaction rate shoots up. That's the power of structure in SN2 reactions. Even small differences can cause huge changes in how fast the reaction goes. Allyl and benzyl halides are in a class of their own when it comes to SN2. They react way faster than regular alkyl halides, thanks to something called conjugation. Here's what's going on. When the nucleophile attacks, the carbon forms a transition state, where it's briefly bonded to 5 groups. That central carbon starts to take on sp2 character, and a p orbital starts to form. Now here's the cool part. That p orbital overlaps with the nearby pi system, either the double bond in allyl or the benzene ring in benzyl. This conjugation spreads out the electron density, stabilizes the transition state, and lowers the activation energy. That makes the reaction faster, sometimes even faster than a regular primary alkyl halide. But not every substrate works for SN2. Some are just structurally wrong for it. Take vinyl halides, for example. The carbon-halogen bond is sp2 hybridized, so the nucleophile can't do a proper backside attack. On top of that, the nearby double bond is electron-rich, and it actually pushes nucleophiles away. So the result? Vinyl halides are basically off-limits for SN2. Aryl halides run into a similar problem. In these molecules, the halogen is bonded directly to a benzene ring, and that carbon is sp2 hybridized. So just like with vinyl halides, there's no room for a backside attack. But it doesn't stop there. The carbon-halogen bond in aryl halides is even tougher to break. Why? Because of resonance. That bond takes on partial double bond character, making it stronger, shorter, and way less reactive in SN2. Now let's talk about bridgehead halides, and these are a different kind of challenge. Here, the leaving group is stuck at a bridgehead position in a rigid, bicyclic structure. And the problem? There's no way for a nucleophile to get in from the back. If you look at the side view, you'll see the backside of the carbon is completely blocked by the ring system itself. That makes backside attack impossible, and no inversion means no SN2. So with bridgehead halides, the SN2 reaction just doesn't happen. At the end of the day, it all comes down to steric hindrance. If the carbon is easy to reach, the nucleophile can attack smoothly. The transition state is more stable, and the reaction runs fast. But if the area is crowded, the nucleophile can't even get close. That extra bulk raises the activation energy and slows the reaction way down. This is exactly why some substrates are great for SN2 and others don't stand a chance. Now let's talk about leaving groups and how they affect SN2 reactions. A good leaving group is key. It makes the whole process smoother and faster. So what makes a good one? It should be a weak base, something stable on its own once it leaves. In other words, it's usually the conjugate base of a strong acid. Why does that matter? Because after it detaches, you want it to stay gone, not come back and mess things up. And here's another tip. For SN2 to work well, the leaving group should be a weaker base than the nucleophile. That keeps the reaction moving in the right direction. Let's rank some common leaving groups, from best to worst. At the top, you've got iodide, bromide, and chloride, classic halides that leave easily. Then there's hydrogen sulfate, tosylate, and even water, all stable once they're out of the picture. A step down, we've got moderate leaving groups, like acetate and ammonia. They can work, but not as well. Then come the poor ones, hydroxide and methoxide. They're strong bases, so they don't leave without a fight. And at the very bottom, amide anion, hydride, and alkyl anions. These are way too reactive. They almost never act as leaving groups in SN2. Let's see what this looks like on an energy diagram. With a good leaving group, the activation energy is low. The nucleophile comes in, kicks it out, and the reaction flows. But with a poor leaving group, the energy barrier rises. The reaction slows down, or might not even happen. Why? Because the leaving group doesn't want to leave, and that makes the transition state unstable. So here's the bottom line. A good leaving group lowers the energy barrier and gives your SN2 reaction a real chance to succeed. Now let's talk about solvents and how they affect SN2 reactions. The solvent you pick makes a big difference. It affects nucleophilicity, reaction speed, and even whether the reaction works at all. SN2 reactions work best in polar aprotic solvents. These don't hydrogen bond with nucleophiles, so the nucleophile stays free and reactive. But in polar product solvents, the story's different. They hydrogen bond heavily with nucleophiles, surrounding them and holding them back. So instead of attacking, the nucleophile gets stuck, and the reaction slows down. Let's make it more concrete. Compare bromide in water versus bromide in acetone. In water, a polar pronic solvent, Br- gets trapped in a shell of hydrogen bonds. It's stable, but not very reactive. In acetone, a polar aprotic solvent, there's no strong solvation. Br- stays free to attack. That's why the reaction runs much faster. So what kinds of solvents work best for SN2? Here are some go-to choices. Acetone, dimethylformamide, DMF, tetrahydrofuran, THF, acetonitrile, CH3CN, and dimethyl sulfoxide, DMSO. These are all polar aprotic. They don't strongly solvate anions, which means nucleophiles stay reactive, and that's exactly what you want. Let's compare some actual reaction rates in different solvents. In methanol, the reaction is super slow because the nucleophile gets heavily solvated. Water's a little better, but still not great. Now switch to DMSO, DMF, or acetonitrile, and the reaction gets much faster. Use HMPA? It's even faster than that. So what's the takeaway? Polar aprotic solvents give you the best shot at a fast and efficient SN2 reaction. Let's take a look at this energy diagram to see how solvents affect SN2 reactions. The key difference? Activation energy. In polar protic solvents, strong hydrogen bonding stabilizes the nucleophile. That makes it less reactive and raises the energy barrier. But in polar aprotic solvents, there's little solvation. The nucleophile stays free and reactive, so the activation energy drops and the reaction speeds up. Bottom line? Polar aprotic solvents lower the barrier and help SN2 reactions run faster and smoother. And that wraps up our look at the three big factors that control SN2 reactions: the substrate, the leaving group, and the solvent. Less steric hindrance? Faster reaction. A good leaving group? Makes substitution easier, and the right solvent, especially a polar aprotic one, keeps the nucleophile active and lowers the energy barrier. When all these pieces line up, SN2 reactions are fast and efficient, but if even one part is off, the reaction slows down or doesn't happen at all. Thanks for watching, and I'll see you in the next lesson.